Fissile Locks by Dave Dice, speaking, and Alex Kogan. Both of us are members of Oracle Labs based in Burlington, Massachusetts in the US. Quick coverage of the agenda. We'll describe the tension between two existing classic locks, test and set locks, and MCS. That'll give us some background and some motivation, and the attributes will inform the design of Fissile Locks. And then we'll get into Fissile Locks proper, the algorithm and its performance, and then we'll end with an interesting addition to Fissile Locks where we can provide FIFO support for certain selected requests. So, test and set locks. These are extremely simple locks. They use an atomic instruction, read, modify, write instruction to acquire the lock, and a store to release. If there's contention and a thread has to wait, it uses so-called busy waiting or spinning. There are a number of variations on this. A very simple form is the simple test and set lock. This is so-called impolite lock. It simply loops, retrying the atomic until it manages to acquire the lock, at which point you're done and you can enter the critical section. Test and set locks suffer from excessive cache write invalidations from those failed atomics, however. We can do a little bit better, though. We can use test and set locks. These are so-called polite locks. They use polling. And in this form, we busy wait or spin using a load instruction until we see that the lock is clear, and only then try the atomic instruction. We should define a term of art here too that's useful. If a thread T1 is waiting on some lock L, and T2 arrives to acquire L after T1, but T2 is admitted before T1, then we have an instance that we call bypass. Test and set locks, the whole family, admit unbounded bypass, and that can give us starvation, unfairness, and progress issues. The root cause of this unfairness, there's a number of origins. It can be hardware, down in the hardware with cache line arbitration, or it can be in the mode of the back off, and we'll describe that a little bit. So, test and set locks. They use global spinning, and by global spinning, what I mean is if we have 10 threads waiting on a lock L, they'll all be busy waiting on that same on a single location. And so thus the store in the unlock must invalidate multiple caches, and there's a propagation latency through the coherence fabric. So we generate lots of coherence traffic, and that can result in scalability failure. To attempt to mitigate the global spinning, we can attempt to use a backoff. And what that means is we loop, waiting to try to acquire the lock. We'll inject delays. This is the backoff. A typical form of backoff is truncated binary exponential backoff with randomization. Exponential in this case means that we double the backoff delay period every iteration, as we're in a given lock acquisition episode. And truncated means we only increase the delay period up to some cap. And randomization helps to avoid certain cases of entrainment where threads can operate in phase with each other. It's worth noting there's a Matthew effect here that exacerbates our fairness concerns. Certain threads may have waited for a long time, and the longer a thread has waited, the deeper and longer its backoff is, and therefore the less odds that thread has of acquiring the lock in unit time. So in a sense, we've stratified the threads into the haves and the have-nots. So we have a trade-off in tension. Backoff improves throughput, but it actually acts against our wishes in terms of fairness. It increases unfairness. Another issue with backoff is we can have dead time or handover responsiveness. So if a thread's waited a long time, it may have increased its backoff delay to some large value. When we finally unlock, that thread may be sitting around on a backoff, and it may take a long time for it to come out of its backoff delay and check the lock again, in which case we have some dead time where that thread could have actually gone in and have tried to acquire the lock. MCS locks. Okay, these are the classic gold standard Mellor Crummey and Scott locks. These are used widely. Arriving threads enqueue elements onto the tail of a linked list with an atomic swap, and we end up with a queue-based lock. These elements form a queue. Threads, once they've enqueued their own element, busy wait on a field within that element. This is local spinning, and by local spinning, what I mean is at most one thread busy waits on a given location at a given time. The benefit to local spinning is at unlock time, when we actually store into that location, only one remote cache needs to be invalidated. Because it's local spinning, no backoff is required, so we can busy wait very aggressively, which decreases the dead time concern and other issues. There are no tuning parameters in MCS, which is very useful. In terms of the queue, The head of the queue is the owner, and that's implicit. The tail is actually an explicit variable, and we need an explicit tail, so that's where threads can enqueue themselves there. Since it's a queue, it's FIFO, which is useful. And we have, as mentioned before, there are queue elements required, and we need one active queue element for each lock that a thread holds, and one for each thread that is waiting on a lock. We also, at unlock time, we also need to reclaim those elements. So what are the benefits to MCS? What are the problems of the MCS relative to test and set locks? Well, first of all, MCS has higher latency than test and set locks or test and set locks under light or no contention. There's simply a longer path with more shared accesses. More specifically, more cache lines are accessed. MCS is also far less graceful than test and set locks under preemption. And the reason is with MCS, we can hand over ownership to a thread that has been preempted. Whereas with a test and set lock, when a thread claims the lock, we at least know it was active and not preempted at the time of the handover. MCS also has queue element management and lifecycle complexities. In addition, we have the classic APIs for lock and unlock simply pass the lock address and don't provide any way to pass any additional information. MCS, however, needs to convey the owner's queue element address from the lock to the unlock operator, which in turn incurs additional overheads and complexity. So, where do MCS locks shine? Well, very specifically, they scale better under high contention. They use local spinning, as noted before. It's fair, FIFO. It requires no back-off tuning, and it's arguably less sensitive to hardware idiosyncrasy. Comparing the two, where do they come out roughly equal? Footprint, certainly. Both are compact and only need, ignoring the queue elements, there's only one word required for the lock body in both cases. It's very common to find convergent evolution. Software projects undergo a common trajectory. They'll start out with a test and set lock, then they'll switch to MCS. This has happened in the Linux kernel, for instance. So now we'll switch over to an MCS variant that was developed by my co-author Alex Kogan and myself and was published in Eurosys 2019. Again, as mentioned, this is an MCS variant, but what we do that's different than MCS is we edit the MCS chain at unlock time, and we look forward into the chain, and we cull or remove remote threads, remote being a thread that's running on a different NUMA node, and move them out of the primary queue and into a secondary queue. And this reduces the so-called rate of lock migration between NUMA nodes. And let's define lock migration. We say if a thread on node 1 acquires lock L, and then the next thread to acquire that L resides on N2, that's an instance of lock migration. And the cache lines, both for the lock and the data protected by the lock, can slosh between the NUMA nodes, and that's undesirable. We want to reduce that migration rate. So at the same time we want to reduce migration, we also want to avoid indefinite starvation. So what we'll do is occasionally flush the secondary queue and change the preferred NUMA node. So what we have is a trade-off between short-term fairness and improved throughput. And by the way, that's common for all NUMA-aware locks. CNA imposes extra duties that we hold while running the lock, and this can give us a scalability impact. As noted, we look forward into the chain, we cull, we flush. There are additional activities, and all those activities occur while we hold the lock. And I should also note that we have a Linux kernel change set under submission to replace the standard spin locks in the Linux kernel with CNA. So we'll switch now to Fissile Locks, the algorithm, and its performance evaluation. So what are we trying to do with Fissile Locks? Very, very briefly, we're simply trying to capture the best attributes of both the test and set locks and the MCS lock. So, Fissile Locks, what do we do? Each Fissile Lock consists of two distinct sublocks. We have an outer test and set lock. This is a very simple, NUMA-oblivious lock. Acquiring the outer lock confers ownership of the composite Fissile Lock. We also have an inner CNA lock that's MCS aware. So, how do we acquire a Fissile Lock? We simply, arriving threads, try to acquire the outer lock via compare and swap. If that compare and swap was successful and they acquired the outer lock, they're done. They enter the critical section. We call this a fast path acquisition. If, however, They didn't manage to get it from the fast path. Then we vector into what we call the slow path, where they have to acquire the CNA inner lock. One interesting aspect of our design is that our tune elements can be allocated for CNA, can be allocated on stack where they cannot be done in the normal case for MCS lock. That gives us another complexity advantage. Once a thread has acquired that inner lock, we say it is the alpha thread. And at any given time, there is at most one alpha thread. All waiting on a Fissile lock except the alpha is on the CNA inner lock. We busy wait. Once a thread has become the alpha, then it busy waits on the outer lock. And again, there's at most one thread busy waiting on the outer lock at any given point in time. Having acquired the outer lock, we then drop the inner lock, we execute the critical section as normal, and then we just release the outer test and set lock with a simple store. It's worth pointing out that no matter how we acquired the Fissile lock, be it the fast path or the slow path, the unlock is the same in both situations. So one thing that we, as described there, we could still have unfairness and unbounded bypass over the test and set lock. So what we do is we intentionally impose bounded bypass. So if the alpha thread waits too long, it becomes impatient after a grace period. And the duration of that grace period is a tunable knob. It's a parameter in our lock and it basically reflects the trade-off between throughput and fairness. After a thread has become impatient, the next unlock passes ownership directly to the alpha. And this avoids starvation. And we inhibit bypass over the outer test and set lock. Fissile locks allow us to use a very specialized form of CNA. In normal CNA, we reorganize the main chain and perform the additional CNA activities in the unlock operation while still holding the CNA lock. What we do in Fissile locks, though, is we perform the reorganization activities early, immediately after having acquired the inner lock. And we can do that instead of late at unlock time as in classic CNA. And what this gives us an advantage. The reorganization is performed outside and before the outer lock critical section. And this improves scalability and reduces the path executed while holding the outer lock. So let's talk a little bit about bypass. Normally when we're talking about locks, bypass is considered a negative. That's actually not so though. Bypass allows us to provide a fast pass for the uncontended mode, and that also allows us to provide, for uncontended operations, latency equivalent to a test and set lock. Bypass also, in a sense, gives us a pressure relief mode when we have contention. So let's say we have a very short critical section with a very high arrival rate. We have intense traffic. Well, in that situation, CNA, if we're just using plain old CNA, not Fissile locks, CNA overheads can come to dominate. This can particularly be the case if the CNA overhead costs are high relative to the critical section length itself. In other words, we have a very short critical section. But bypass, as we find in Fissile, provides an alternative entry, and it's not strictly gated by the CNA path. I should point out that even with bypass, CNA still acts to filter out the set of circulating threads. And in a sense, CNA homogenizes, we have enough threads passing through the inner lock that it homogenizes and reduces the set of active circulating threads and reduces lock migration. When this critical section is long and we have lots of waiting threads, Fissile just devolves to CNA, and the Fissile aspect neither hurts nor harms. I'll now describe a micro benchmark that illustrates a number of these points. The following benchmark spawns a number of concurrent threads. Each thread loops. It acquires a global lock, runs a short critical section, releases the global lock, executes a non-critical section, and as noted before, it simply loops doing that. At the end of a timing period, we report the aggregate number of iterations completed by all the threads collectively. On the x-axis, we have the number of threads, and on the y-axis, we have the aggregate throughput. I should note that both of these are log scale to allow us to show some of the more interesting effects more clearly. This benchmark was run on a two-node system, Intel Xeon. Each node has 18 cores. Each core has 2 hyperthreads. So we have a 72-way logical system. Interestingly, performance starts to drop at around 5 threads for a number of the locks as busy waiting and contention start to take effect. We can see that the 2 NUMA-aware locks of interest, Fissile and CNA, actually start to recover performance at around 16 threads. And the reason they start to rebound is that we have sufficient number of waiting threads that we can pick a local thread to hand the ownership off to, and therefore we reduce lock migration. And we basically have enough waiting threads when we hit about 16 threads total. Also of interest in this is the fact that we can, beyond 72 threads, we start to encounter preemption starts to be active, and we notice that most of the threads suffer degradation, but Fissile actually manages to, because of its test and set nature, manages to avoid the complete meltdown observed in CNA and in MCS. So we'll now discuss very briefly extended FIFO support for Fissile locks. So if Fissile allows us to allow some lock acquisition requests to run with in an expedited mode. And what we do is if we can identify a request either by the thread, say perhaps it's priority or special locking API, if we can identify an expedited request, when that thread arrives, we simply try the outer thread as usual, the outer lock as usual. It's a simple trylock. But if that expedited service request thread must wait, it then disables all avenues of potential bypass. And there's 2 types of bypass. We'd have bypass in the inner lock, and to avoid that, we mark the CNA queue element as uncullable. In other words, it can't be pulled off the chain. And we disable bypass on the outer lock. Details of that specifically are in the paper. But this results in FIFO-like behavior for expedited. And finally, if you have any questions, feel free to contact me. And there's a longer form of this paper available on arXiv. Thank you.